Okay, hello everyone, and hope you're all doing well. And welcome to the IOP webinar. Today, we have an exciting talk that we're hopefully going to see and hear today. But before we go into that, I wanted to introduce our speaker, our esteemed speaker, Jorge. He's currently an associate professor at the Faculty of Science at the University Autónoma de Madrid. He leads the research group working at the interface between material science and artificial intelligence. He got his PhD in condensed matter from the same university in 2006. He has worked as a postdoctoral researcher at the MIT from 2007 to 2010. And during 2018 to 19, he was also appointed as a visiting professor at MIT. He has co-authored over 60 scientific articles in several book chapters and has been an invited speaker for over 20 international conferences. He's a co-inventor of 3 international patents and a lead PI or co-PI of 4 projects at the competitive national and international calls. In 2013, he was awarded the MIT TR35 Spain Prize as one of the top 10 Spanish innovators under the age of 35. And he's also the founder of the Spanish Network of Artificial Intelligence for Condensed Matter Physics and Material Science. So thank you very much, Jorge, for coming over and giving us this talk. So we're all looking forward to that. So I'll pass the floor to you.
Sure. Thank you so much, Prashant, for the nice introduction. Let me share the screen. Okay, so thank you so much. It's my pleasure to be here. Thank you, Fabrice and Prashant, for the invitation. And in this talk, I'm going to tell you about AI for physics and physics for AI. Let's see what that means. So first, let me provide a very quick introduction to my research group at Autónoma. We are a small research group that we are exploring how AI techniques can actually accelerate and help advance condensed matter physics and material science research. We are working on 3 main topics these days. We are working on machine learning assisted material discovery and design. We are working on novel AI hardware platforms based on our condensed matter physics insights. And we are working on a 3rd topic that has been a lot of fun, that is trying to open the black box of deep learning methods, trying to understand how they work so well and how what can we do to tweak them a little bit. And in order to tackle all these problems, basically, we apply a variety of techniques. We use a lot of what we call vanilla neural networks that are then simply densely connected neural networks. We use convolutional neural networks. We use some algorithms that we have discovered recently that are invertible neural networks that turn out to be really powerful and versatile for inverse design. We do also a lot of graph neural networks, and we have been working a lot also on what people are calling these days scientific among some other techniques. Of course, all this work is being done by a small group of very bright PhD students and a group of excellent collaborators. Let me mention PhD students. Iñaki Garcia, he's co-advised with Professor Alejandro González Tudela. Michel Friesing, that he's co-advised with Professor Ferrer Prince at Autónoma. And also at Autónoma, I'm working with Juanjo García Esteban, this PhD student, also co-advised with Juan Carlos Cuevas in this case. So here is an outline of this talk. First, I'll provide an introduction, an overview of what I mean by AI for physics and physics for AI. And after that, I will provide 2 illustrative cases that I hope can give you a hint of the potential of these techniques in very different areas of material science, and I will end up with a summary of the main ideas. So, but first things first, let's talk about the distinction between AI, machine learning, and deep learning. So there are many definitions of artificial intelligence out there in many sources, but the one I like the most is this very general definition provided by Russell and Norvig in pioneering actually reference, Artificial Intelligence, a Modern Approach. Basically, they state that AI is essentially the designing and building of intelligent agents that receive presets from the environment and take actions to affect that environment. So it's a very general definition in which essentially you have some intelligent agents that take actions, and that actions are affecting the environment. So it's very general. But it's also important to distinguish between the two main categories of AI. We have artificial narrow intelligence, that is where all the action is happening these days. This field has developed very fast in the last decade. And all the news that you see in newspapers, in the media, are actually connected to this particular category of AI, that is essentially the building or designing of one-trick ponies, if you will. So you design systems that can do very well a single task, but just a single task, and so well that they can outperform easily humans in that particular task. And on the other hand, we have artificial general intelligence, that is a field that has been moving slower than artificial narrow intelligence. It's an amazing field, the development of a system that can do or can learn to do very well several tasks at the same time. But here in this talk, we will be always concentrating in this particular category. Okay, so within artificial intelligence, we have a sub area that is called machine learning. So one can define machine learning as the field of a study that gives computer the ability to learn without being explicitly programmed. For somebody like me that has been working in computational science for 21 years already, this is an amazing definition, right? Because this is a definition that tells you that there are computers that can learn without the need of, without you having to type rules or instructions in the computer, right? So let's think a little bit about what that means from a research problem. Usually what all of us scientists have been doing, at least in this computational science area, basically we study the problem, we build some physical model, and we write some rules, right, describing that model and the application of that model to a particular system. You write those rules in the programming language you prefer, like C++, Fortran, Python, whatever. Then you run that code and you evaluate the solution. The solution is fine, or you are happy with it, and it seems to make sense. You basically essentially publish a paper, right? But it can happen that most of the times, the first time you try to do this, it doesn't work very well, and then you have to study again your problem, revisit your set of rules, meaning revising your model, and then going over these loops, a few times. Well, essentially, when you are in the machine learning mindset, essentially you have to focus on this pink square in the middle, the right rules square, and replace that by a different source. Essentially, you replace that by data and an algorithm feeding that you feed with that data. That data has to satisfy the criteria of volume, veracity, and variety. And the algorithm basically is going to extract knowledge from that data set. And in that sense, that spirit is very different, because you don't have to enforce the rules that are describing the problem. You just need the algorithm to find those rules. And surprisingly, sometimes you don't even code the machine learning algorithm. You sometimes take that algorithm off the shelf and tweak it a little bit, but it's not the main point. And the rest of the process is the same. There is another difference, that the solution that you are reaching is an approximate solution. But you will say, hey, in any problem that I've been working on with computers, all solutions are approximate, because my model has approximations. I have to make a discretization of my system, whatever. But here I'm talking more about approximate solutions in a statistical sense, in the sense that instead of getting a definite answer of what the solution of your problem is, you get a distribution of probabilities of what your answer can be. For instance, you can be studying a problem in which the machine learning algorithms is providing a probability of 90% that the energy of your system is going to be 1 electron volt, let's say. But with that prediction, it will come a distribution of probabilities with some other energies of your system. So whenever you are applying machine learning to a given problem, you really need to basically have this different mindset. Okay, and of course, within machine learning, we have another sub area that it is called deep learning. That is essentially the use of artificial neural networks that can adapt and learn from large amount of data. Actually, here is an important point to make, that is that deep learning is actually growing so much in popularity and being so powerful and versatile these days, that it's essentially eating up the whole artificial intelligence scenario these days. And I will tell you a little bit of why is that. So one of the reasons is these days something is happening, right? Why deep learning in particular is taking off so quickly. And this is a relevant question, particularly if you take into account that AI is actually an old topic. Not so many people are aware of this, but it's actually a very old topic. AI, the term was coined in the 50s. The first prototype of a neural network actually was developed almost in 1960. Everything was hardware by then. And the main ideas of deep learning actually come from computer vision from the 80s and the 90s. So also AI, usually people tell that is the history of the next big thing, in the sense that it was gaining popularity in the 60s with what people call the good old-fashioned AI. But after that, there was some winter of popularity. Then the second boom of popularity happened in the middle 80s, and with the expert systems, and again the interest decayed eventually. And from a few years before 2010, actually some people say that we are living the ultimate takeoff of machine learning, actually, due to essentially deep learning and due to the amazing applications, autonomous vehicles, and many other applications. So this is happening because if you think about that, AI is living at the intersection among three different areas: computers, data, and algorithms. So what is going on is that all these three areas has been developing in parallel at a very fast pace. Big computers, all we know about this amazing technology of GPUs that NVIDIA is developing in a very fast way. big algorithms. There are many people developing extremely good algorithms. Perhaps their the backpropagation algorithm is the flagship algorithm in this context. And big data, what I can tell you about big data, all of us have a data collector in our pocket these days, right? So, but here I wanted to make a point that is actually, I think is important. Is essentially the fundamental different behavior of deep neural networks with respect to data in comparison with traditional machine learning. So if you plot somehow the performance of your algorithm in whatever metrics you want in terms of how accurate it is, how general it is as a function of the amount of data, and you consider traditional machine learning algorithms and neural networks, starting from shallow neural networks up to deep neural networks, you realize that deep neural networks are behaving very nicely with data. Traditional machine learning plateaus very quickly with the amount of data, but deep neural networks can actually swallow a lot of data at the same time that they are increasing their performance. So this is very good in a lot of contexts. But one has to be very careful when you are doing AI for science, because in a scientific setting, usually you operate, or it happens frequently that you need to operate with just a few experiments, with just some computational data, but it's not the magnitude of data that you have, for instance, in a face recognition problem or something like that. So, and if you see this pink square here, you see that sometimes a deep neural network is not the solution for the problem, in the sense that deep neural networks or deep learning actually can be much less efficient than traditional machine learning if you have not so much data. So this is a point that needs to be taken into account very carefully. So, so let's talk a little bit more about AI for science. AI for science is basically something that is moving very fast these days. These are just the covers of a Nature journal that I collected from last year, with applications in biology, mathematics, in many different areas. But focusing more on chemistry and material science and physics, one experiment that one can do is basically take one of these general explorers of articles, or general tools for exploring articles, and look for papers in material science, chemistry, and physics, for the number of papers, for instance, as a function of years, and see how many papers are also referring in the topic to deep learning, machine learning, and some other related terms, meaning that those papers probably are using those techniques to do some finding, or to achieve some finding in some of these categories. And if you do that, you find that a few years before 2020, there was a change of trend. Essentially, the article count in which some people was doing research in material science, chemistry, or physics, and using machine learning actually started growing very fast. And this is something that is also obvious if you plot the percentage of the total amount of articles that are published in these categories as a function of year, and you do a similar search, you will find the same trend. But if you do some kind of rough extrapolation, in this case, something like really rough, one can start thinking that soon a significant part of all papers published in these categories can actually be making use of machine learning or deep learning as a part of their work, essentially. Of course, in the physical sciences, people have been working on machine learning for some time now. There are really, really good reviews out there. These are just 3 of them that are particularly appealing for me, but there are many. So when you start working in this area for some time and you start reading literature on the topic, somehow you start having a clearer sense of what are the usual or the typical problems where you expect that machine learning or deep learning can work. And this is my personal take on that, okay? But let me tell you about that. So, okay, so there is a category of problems in which machine learning or deep learning is usually useful, that are classification problems, in which it would be unrealistic or unknown how to write a specific set of rules by hand. For instance, imagine that you are predicting some spectra, and that spectra, some signal as a function of frequency, has so many peaks, and it has a lot of variety of phenomenology. So in that case, it's kind of almost impossible to describe everything that happens there by hand, right? Just by typing instructions in a computer. So in that case, it's much better to let a machine learning algorithm to learn the knowledge to that. Then there is this second category, surrogate models, that are actually models, machine learning models, predictive models, that are created in order to speed up simulation, like, for instance, a multi-scale simulation. Of course, you pay the price that you get these approximate solutions I was telling you about before, but still, in some areas, they make a lot of sense. And then you have a third category that are inverse design problems. Inverse design is the process in which we have some targeted property or some targeted functionality of a device in mind. And then we need to find the parameters of our material or our device that can lead to that particular response. That is something where deep learning can be very helpful. And also a fourth category is dealing with noisy data. Essentially, deep learning, or actually machine learning in general, can be very efficient, basically dealing with noisy data because they can see through noise, essentially what's going on. So as I was saying, let me provide a couple of illustrative examples. The first one is the application of deep learning for nanophotonics. And let me tell you why I think nanophotonics is a suitable playground for machine learning. So nanophotonics is one of those fields in which it is easy to get a point-over-point agreement between theory and experiments. And this is quite unique. This figure that you see in the slide is just for illustration. Don't worry about the details, but just it is there just to make this point. So essentially, this capability allows you to create training sets in a computer, to explore algorithms in a computer. That later you know that they are going to work with experimental data. And that's a very important way to develop also algorithms. So in that sense, machine learning is a tool for solving nanophotonic problems, but also nanophotonics can be used, as I was saying, as a playground to develop novel algorithms. And of course, many people have realized about that, and there are already quite a lot reviews out there. Again, these are just a sample. But let me walk you through some illustrative problem that can convey, or I think can convey the potential of these techniques in this particular area. So as I was saying, there are these four main categories. But something that is important to realize is that these categories of problems, they are not independent, in the sense that most of the problems can actually be ascribed to several of these categories. For instance, the problem that I'm going to tell you about has some aspects in which you use surrogate models and some aspects in which is a kind of inverse design problem. So let me provide a bit of background regarding the problem that we need to solve. I mean, I'm not going to enter in domain expertise details, but let me just tell you that 25 years ago, it was found that an array of sub-wavelength, meaning smaller than the wavelength, holes arranged in a periodic way in a metallic screen, in an opaque metallic screen, actually that set of holes can transmit much more light than the one corresponding to having those holes working independently, to the point that they can make the metal film to look transparent or almost look transparent for a given set of wavelengths. This is a resonant phenomena. So, well, I mean, it was found, the physics of this process actually was discovered later on. And actually, it was found that it's a kind of tunneling of photons between some localized states that are living in the surfaces of the system. Well, so also it was found that if you make a single sub-wavelength, a tiny hole in a metallic screen, and you surround that tiny hole with a periodic range of correlations, then you can get similar effects. And people call this effect a resonant transmission of light. So in this talk, I'm going to focus on this particular system that is just a slit perforated in a metallic screen that is surrounded by corrugations to the left and right. So, well, this is just a sketch of how is our model system. You have a tiny slit surrounding to the left and right by corrugations. At the illuminated side, the light is coming from the top, and also corrugations on the non-illuminated side of the metallic film. What is the main challenge here is that even for domain experts, it is difficult to figure out how to simultaneously tailor the system to have a spectral, directional, and polarization control of the light that is transmitted through the system. So even for experts in this area, it's kind of difficult to say how you need to tweak the geometry of the system to get a given response in terms of all these properties at the same time. So the main idea that arises in this context is that why not solving this problem learning from data? So the first thing, well, this is the proof of principle problem that we are using for exploring this this solution, in which we are basically considering just the input side corrugations that are the ones associated, that we know are the ones associated to the spectral control in the system. So this is learning from data. The first thing that you need to do is to create a data set, right? As I was telling you before, in nanophotonics, you can create your data set in silico, because you know that that data set is going to be is going to go hand by hand with the experiments. So we created this data set with the geometrical parameters that are accessible experimentally, and essentially in order, so these are a bit technical details, but in order to create them, we have to use our home-made theoretical model that actually allows us to create 600,000 spectra for our data set. So this is a lesson for us, actually, because it turns out that sometimes the conventional methods, or the most popular methods, numerical methods, to solve this, the physics of this problem, actually are not suitable to create the kind of large data set that we need in our case. Because these conventional methods are extremely powerful, but they have this drawback that they need a lot of human intervention. So in the case of if you want to create a large data set, essentially you need to have accurate calculations without the minimal human intervention. Because imagine if every spectrum that you generate from the system needs to be checked one by one, right? So when once we have created our data set, basically what we did is to take each of the spectrum, each of the spectra that we generated, the transmission as a function of the wavelength. This is a single spectrum corresponding to a given set of geometrical parameters defining the system. And we basically, what we did is we sample that spectrum in a number of wavelengths. In this case, we were using a sampling of 81 wavelengths in order to reproduce well all the details of each spectrum. And then the problem became, the problem of predicting this spectra became, given a set of geometrical parameters defining the device, what should be the numerical algorithm that can do a good mapping to the right values of the transmission in the sampling that we are doing, right? So this mapping actually is something that we did using a deep artificial neural network in which the input layer are the geometrical parameters and the output layer are the values of the transmission that we are sampling. And in the middle, we have a set of elements called hidden layers. Each of one is formed by artificial neurons. So what artificial neuron does? So essentially, it takes all the information from all neurons of the previous layer of your network, and basically it applies to it a nonlinear operation that has some parameters, the weights and biases, and some activation function, and then it propagates that information to the next to the neurons in the next hidden layer. So essentially, this is a problem of minimization of the so-called loss function that basically measures the distance between your predictions for the transmission and the ground truth of those predictions. Measure that distance and tries to minimize that with respect to all parameters defining your network, the weight and biases that can be sometimes can be millions of parameters. In this case, it's not so large, but you have to be have a method to do this kind of optimization, and this is where backpropagation enters into play. But I won't be entering too much into that. Let me just say that in order to do this optimization right, you have to tweak the parameters of your algorithm. And in deep learning, these are machine learning in general. These are called hyperparameters. There are some of them associated to your network architecture, like the number of layers, number of neurons per layer, the activation function, or weight and biases initialization. Those are the ones that you have to touch in order to define your network architecture, or the hyperparameters associated to the neural networks algorithm itself, the epochs. One epoch is the number of epochs is the number of times you go through the whole training set, the batch size, and or the learning rate. So let me tell you, so just to be clear, you understand everything in this work through this application of deep learning. Let me tell you a little bit about the interplay between training, this hyperparameter tuning, and the final assessment of the model performance. So essentially, in this case, or almost in any problem in deep learning, you start with some original data. In our case, is this 600,000 spectra, and you divide it in 3 groups: the training data, the validation data, and the test data. So you take the training data, and with the training data, essentially, you find the optimal weight and biases that are minimizing your loss function, that are minimizing the distance of the predictions of your network with respect to the ground truth solution. This is supervised machine learning, so your training set is labeled. And then you use some validation data, part of the training set, that is not part of your training set, is part of the original data, and then you use that to tune the hyperparameters of your model, to make your model better. And once you are sure that your model is quite accurate, you essentially need to somehow assess the model with data that the model has not seen before. Because remember that the goal of deep learning at the end is to make predictions on things that are not included in the training set, because what would be the purpose of being very accurate for something that you know already, right? And in order to do that, basically you use some part of the data, of the original data, that it is called test data, that your algorithm has never seen before, to avoid this leakage of information problem. And then you use that test data to provide a final number of the performance of your model, again, with data that it hasn't seen before during the training process. So there's there's a lot of work to do when you do this hyperparameters optimization. You need to look at the dependence of the loss function, the evolution of the loss function with the number of epochs for different activation functions. There are many of them, and you need to be careful to do this in a systematic way. We did it for this device, optical device I was telling you before. These results corresponds to that case. Also, for the optimizer that is minimizing the loss function, there is this optimizer, it is called Adam, that is extremely robust, and there are theoretical reasons in this context. There is also the optimization with respect to the learning rate, the optimization with respect to the architecture of the artificial neural network, the number of hidden layers, the number of neurons per hidden layer, and so on. Well, at the end, you can complete this training process in a very systematic way, and you can be quite happy with the result and so on. But the performance of your network is actually proven in the inference mode. Again, when it is deployed to make predictions for samples not included in the training set. In our case, those samples are actually spectra. So let's see how that works in our case. So once we have optimized the algorithm, essentially what we did is to plot the number of the normalized value of the loss function as a function of the number of epochs. This is the so-called learning curve that is to the left in the slide as a function of the training samples. The blue line corresponds to the larger number of training samples. And we see that after some plateau here, it basically decreases very quickly. And actually here, I'm showing the transmission as a function of wavelength, the spectra, for some illustrative cases. The comparison between the predictions from a simulation done with this coupling theory I was telling you about. Those are the solid lines, and the dashed lines corresponds to the predictions for from the artificial neural network. And then this is just a visual representation that actually is kind of a point-over-point agreement between the predictions of the artificial neural network already trained with the coupling theory results. But still, you can do better in the sense that you can do a quantitative assessment of how good your model is, calculating the average prediction error per wavelength, per spectrum, for this 10% of the 600,000 samples I was telling you about before. And then you see that is less than 0.5% in this case. So it's a quite accurate device, numerical device. So, but the next natural question that arises in this context is that, okay, I have a artificial neural network that is able to give me a prediction and an accurate way, a prediction of what is the transmission given some geometrical parameters on my system. But what about if you have in mind some spectrum that you need for some specific functionality, and you need to find what are the geometrical parameters of your system that are leading to that spectrum. So this is an inverse design problem, and the first idea that comes to mind is why not training the artificial neural network in reverse. Before we have the geometrical parameters leading to a given spectrum, why not training a network in which you plug the sampling and you obtain the geometrical parameters leading to that spectrum. But doing that is problematic. In this case, because the solution is not unique due to symmetry in the problem. So one needs to find a more sophisticated solution, and we came up with this tandem neural network solution that actually is working quite well. So it is based on two stages. One stage is trainable, and the one surrounded by the dashed blue lines, and the other one is not trainable. It's a feed-forward artificial neural network that we have trained before to provide the spectrum corresponding to a given set of geometrical parameters. So when you plug these two stages together, essentially you can feed this first layer of your system with the sampling of the targeted spectrum and look at how your system basically is propagating information until you end up with some prediction of how the system thinks that the spectrum propagates through the system. So essentially, doing this kind of process, we are making sure that if you are using the right loss function that glues together the two stages of the tandem neural network, it is possible to avoid this problem of multiple solutions. Essentially, because you are enforcing a single solution by providing the training with the right geometrical parameters. And let me show you how this algorithm works. Once it has been trained, we basically choose a goal that was creating some transmission bands at position centered at 500 and 600 nanometers. And this is what the algorithm thinks is the best the device can do to produce this particular spectrum. Later we did a simulation to confirm that the prediction of the algorithm was right. But at the end of the day, the algorithm was able to guide us towards the right geometrical parameters that can produce something that is the closest possible response to this kind of arbitrary response that we have chosen. So I didn't want to go very long in this talk, so let me take advantage of 5, 7 or 10 minutes to tell you about this second use case. That is something that we are very excited about these days, and is also taking off very quickly. And I wanted to present this in this talk. So this is a completely different problem. So here, this is a collaboration, a very close collaboration that arises, that have arisen between my group and the group of Consuelo Alvarez Galvan, that is an experimental group that is working in the Institute of Catalysis and Petrochemistry at CSIC, also in Madrid, in which basically we are trying to see if there is any way in which machine learning can accelerate the development of new catalysts in the context of sustainability. So the big picture of the problem, one of the motivations why we are jumping into this problem is because we want to make our a small contribution to avoid the predictions in the increase of temperature that current policies and current technologies will be leading us in the next decade. Essentially, due to global greenhouse gas emissions, the increase of temperature that is predicted in different scenarios, even in the most optimistic one, is actually quite catastrophic, right? So, but people are trying to basically to do a lot of work in this area to try to solve this kind of problems that actually involve to everyone, right? So, so basically there is a direction that is the reduction of CO2 emissions using catalytic processes that are leading to new fuels and bulk chemicals. Okay, so the question here is that if you are considering the traditional processes in catalysis R&D, they're really trial and error processes. In the sense that if you need to develop a new catalytic material, it can take several years in the most successful scenario. So the question here is how we can use our knowledge in machine learning for scientific problems to accelerate this process. And the question comes actually by thinking a little bit about the context of this field, right? So in order to control the catalytic activity of some material, you need to engineer that material so you can be able to engineer the electronic structure by changing the composition and the physical structure of your material. That's the key point. You need to start thinking in a different way. You need actually to invert the conventional question that domain experts in the field has been asking themselves for a long time. The conventional question was, or is actually, why particular materials are good catalysts for given reactions, to a different question. To the question is that, imagine that we need to catalyze a given reaction under a specific set of conditions. So which material should we choose? It's kind of an inverse design problem. Of course, there are a lot of work done through systematic computational studies in this area. This is a work that I like a lot, in which they were able to discover a new nickel gallium catalyst for carbon dioxide reduction to methanol just by doing a large number of simulations. The figure shows the turnover frequency of the catalyst as a function of the absorption energy of oxygen on the surfaces of the materials. But the point is that you can do high throughput computational studies and find very good results. But still, we wanted to go beyond that, and we wanted to adopt some technique that in the field is starting to be called active learning, and it's a kind of a little bit involved methodology. But let me take it one step at a time. You start with some database, and in this case, in this particular area, the database is composed of data from the literature, calculations, experimental data. Everything can help, and everything is in that database. And even though usually they are sparse databases, they are databases that in which there are a lot of data in some specific regions. Some other regions are lacking data, so it's a tough problem. So in our case, we were lucky enough to have this large data set from the group of Professor Thomas Blicher in Denmark, that is essentially a large-scale DFT study of chemical adsorption hydrogenation of different species. It has almost 2,000 bimetallic alloy surfaces, 37 pure metal surfaces, atomic absorption of a few species, but also the absorption of those hydrogenated species, and all unique absorption sites were considered. It's an amazing database that contains more than 90,000 systematic DFT calculations, density functional theory calculations. Okay, with that database, basically what we are doing is that we are applying suitable machine learning techniques. Essentially, we are applying a Bayesian approach in which we are combining a multi-descriptor linear regression model with Bayesian information criteria as a figure of merit to select the right model, and with a Bayesian model averaging in order to make the model more robust. Sorry. And this Bayesian approach is actually a lot of fun. There's a lot of interesting things to look at. For instance, given a set of absorbed species, chemical species, with some computed absorption energies, one can apply to a linear regression model to express the absorption energy of one specimen in terms of the others, right? And you use the others as descriptors in this case. Well, as I was saying, it is possible to use Bayesian information criteria to select the model evidence, to select the best model. And then this is working quite well as a function of the number of descriptors. You see the minimum of this Bayesian information criterion, and then to select the right model. So with that, we are basically in the process of creating new stoichiometries and new configurations for new catalytic materials, and proposing them to our experimental colleagues, and essentially corroborating them experimentally. And here is where the active learning loop actually makes sense, because essentially when you do this once, you will get some improvement over your previous catalytic material, but it's not what we are basically finding is not much of an improvement, because at the end this is the first iteration of a loop, in the sense that with those data you can feed your database with the experimental data that you obtain, and then what we are basically witnessing is that actually this is increasing the generalization power of the whole machine learning approach. And this is something that we are quite excited about. This is work in progress. We are targeting two main reactions related with CO2 valorization via syngas production. A reverse water gas shift is one of them. The other is reforming of methane. And we are adding a lot of variety to our database. Particularly, we're considering bimetallic alloys, and then something that we realize is that in our database we can also include possible changes of the geometry, right? How the geometry is affecting the catalytic materials. And I don't want to go much in detail because it's getting a bit late. So here's a summary of the main ideas. Essentially, you have seen how just simple, densely connected artificial neural networks can be used to accurately predict the response and to do inverse design in these devices, optical devices associated to resonant transmission phenomena. And you have seen at least a hint of how active learning approaches, in which you basically combine numerics and experiments all together, can actually or are actually offering quite some potential for accelerating catalyst R&D processes. Okay, so thank you very much for your attention.
Thank you very much. Okay, that was absolutely brilliant. I mean, of course, I've used AI for various different things from my piece of work, but it was really interesting to see some of your applications and the way you're using that. I think that was brilliant. I've got a couple of questions I want to ask, but just wanted to let everyone else know that if you have any questions, then please do add it in the Q&A or the chat, and then we're more than happy to take those. But it was quite interesting to see towards the end. I know you didn't show much around that, but around the active learning side, the circle, which was very, very interesting to see. And you were mentioning that you were looking at repeating that and you were getting improvements. So there what kind of improvements did you see? Well,
I mean, the thing is that this is an area in which slight improvement can have great industrial interest. So basically, we see slight improvements in selectivity, in the activity of the catalytic material, and basically they are just slight improvements. I can tell you that, but one slight improvement actually can put us ahead in this kind of selectivity, activity charts that everybody is using in this area. So, I mean, there are small improvements that actually we are finding surprisingly that they wouldn't be found in the first iteration of the active learning approach. Somehow the ability of going hand by hand the numerics and experiments is giving us some kind of edge in this particular problem, and this is something that we didn't expect. I mean, I'm a computational scientist. I wasn't expect. I'm used to stop when your predictions are corroborated in experimental setting, right? But in this case, you can go beyond that and repeat the iteration. But I can tell you that each iteration is very time consuming and it's a lot of effort, because once you propose a new stoichiometry, you need to synthesize the catalytic material, and then you need to measure you need to characterize experimentally that material. So every iteration, a lot of synergy between the numerical part and the experimental part. But in general, I think the idea is that going in this direction of integrating somehow experiments and machine learning is something that we are doing that with these active learning loops. But the philosophy or the spirit of that in general, I think can solve problems that only with the machine learning part you will get stuck probably.
Okay, excellent. A couple of other things that, I mean, we've probably faced in how we apply machine learning into different problems in my domain. I think one of the key issues and challenges is, of course, always data is an issue. Making sure you have enough data, and you started by talking about that and how that's important. So I think the first question is, if you've got small amounts of data only, what could one do, and what are the kind of techniques? And the second one is more around biasing in data. So bias is always an issue, especially when you're looking at, depending on how you're looking at training sets and things like that. So what can one do in order to try and minimize the effects of bias?
Yeah. So in the case of when you have we are working quite a lot with the small data sets, because AI for science is how it works. I mean, like, we are involved in several projects where the domain experts tell us, well, I have a measurement of the order of hundreds in my lab during the operation of the lab since the founding of the lab, right? But in that case, you need to basically forget about deep learning and apply random forest algorithms, Bayesian approaches, anything that can work well with the small data sets. And actually, it is funny to see, like sometimes we see people using a lot of deep learning techniques in problems that could be much more efficiently solved with more conventional machine learning techniques that maybe they are not so popular, but they're really rewarding in the sense that the computational resources that you need are not so high. And for instance, in this case that with the catalytic materials, we are using definitely Bayesian approaches that are working very well, and we wouldn't probably change that for any other algorithm right now. Mm-hmm. And regarding the other question, well, I mean, this is another area that we were quite concerned about numerical the generation of data sets in a computer, because at the end you generate those data sets with a method, a numerical method that most of the times there is some approximation, even if in the more numerical method you have to approximate the dielectric constant with some function or take it from some tables in the literature. But that's why I think hybridizing your data set with experimental data, with the right descriptors and so on, is key to avoid that and to provide some generalization power, definitely. Yeah.
Mm-hmm. Yeah, we've got a couple of comments that are coming in, or questions, I would say. I think the first one's from Douglas, who's talking around, again, data sets as such and sizes that expectation is that usually you need thousands of new neurons and so on to really come up with some reasonable results from the outputs. So can you comment on that?
Yeah, definitely. This is a good question. Actually, when we started working with these physical devices, actually, to predict the response, we were quite surprised to see, because we were doing a systematic study of what the architecture of the network should be, and we have been also reading all these computer science papers for much, I guess, with problems with much more variety and so on. And we, at the beginning, actually, in some of these problems, David, that was actually another student in my group, he said, okay, I'm going to start with a huge model, like the biggest model I can fit in our cluster. And basically, the good thing of being a physicist is that you think the other way around, right? You start with a minimal model, and if it doesn't work, you start increasing. And we actually were surprised. But at the end, we realized that physical problems, or problems in which you have a lot of physics, have an underlying, an underlying rule governing everything. And somehow the nets, the neural nets, they learn that they don't really need, in this particular problem, maybe there are some other cases that is different, but in this particular problem, we were surprised about how small the neural net is, and we assigned, or we ascribed that to the fact that there is actually some underlying physics that, of course, we didn't introduce that anywhere. This is not physics inspired neural networks, but still. So I think there are more surprises regarding that. So everybody is talking about large models, this kind of foundational models, in social networks. You see this recently, this Dale model, GPT-3, all these huge models. But when you are doing scientific problems, you will be surprised about the size of the models. They are not necessarily to be so large. And this is something that we are reporting also in papers, right? We are reporting the fact that, well, we have found that the data set probably doesn't need to be so large. We found that there is a minimal model in terms of the architecture of your network that can work as well. So that's an interesting point. Yeah.
Excellent. I think that it almost kind of looks at what the next question is from Alex as well, which is how much data do you need for deep learning to start outperforming other methods? I guess that also depends on the kind of problem you're trying to solve,
definitely.
Isn't it? So and like you mentioned, so it's, and like you just mentioned, that for some problems you don't need to even go very deep in terms of, you know, the number of hidden layers and things like that. It could be quite small, so it's almost problem dependent. Okay, Alex, there's another question. Can you elaborate on why deep learning doesn't work for small amounts of data?
Well, it's a matter of sometimes your small amount of data doesn't cover all the variety of your problem. Is what I was telling before about the catalytic materials, is that you cannot choose the regions in which you are exploring the response of your material. You maybe have a part of the regions in terms of temperature, of pressure, or whatever property that you have a lot of data there. But in order to improve your catalytic material, you need to go to some other regions. And there is where deep learning cannot be as helpful as some other algorithm that is guiding you to propose what is the next experiment to do. And for instance, Bayesian approaches are really good at that, at having a small number of data, a sparse data set, and telling you what the next experiment you can do. Deep learning, we love deep learning and we use it a lot, but in particular case of very small data sets, we haven't found. But again, I mean, machine learning and deep learning is a matter of trying things, right? So this is our particular experience. Maybe somebody else can make a neural network work in this context, but for us, this is working well so far.
Brilliant. And actually that does also talk a little bit about what Lawrence put as well, which is around the differences between machine learning and deep learning, not just in terms of amounts of data, but other things. So I mean, that goes back to in terms of what the structure is of deep learning and how it works. It's a subset of machine learning.
Yeah, definitely.
Yeah. Right, brilliant. Thank you so much. I'm not seeing any other questions or comments. So thank you again, Jorge, for coming and taking the time out from your busy schedule and giving the talk. It was absolutely fascinating to see some of the results as well, but also especially the way you used the tandem model as well. So it was really insightful, and I'm sure the delegates would have all enjoyed that. So thank you again.
Thank you so much.
And thank you everyone for who's come and attended this. We will of course be recording this and these will go live soon, so you will see that as well. Thanks again everyone, and hope you have a nice Easter break. Thank you.
Thank you so much. Bye bye.
Thank you. Bye bye. Bye bye.